My name is Joseph Gonzalez. I'm a postdoc in the UC Berkeley AMP Lab, and I'm going to be talking about our work on GraphX, which is a graph processing system built on top of a general-purpose distributed data flow framework. Now, as part of my thesis, I worked on a system called GraphLab and PowerGraph, a specialized system for doing graph analytics. And in this work, we're exploring the task of distilling the essential ideas in these graph processing systems and trying to lift them up to the context of general-purpose distributed data flow frameworks, enabling a single system to effectively span the entire analytics process. And so to motivate why I want to do that, I first want to illustrate what a modern analytics process looks like. So we might begin in our modern analytics story with some raw data. And typically this data is either in some semi-structured or even unstructured form. In this case, perhaps we begin with Wikipedia XML dump. And now if we want to understand what's going on in Wikipedia, we might begin by parsing this data into a table, a link table, perhaps encoding the title of each article and the articles it links to. Now from that table, we might induce a graph view, a hyperlink graph, and then apply algorithms like PageRank to identify the top pages in Wikipedia. So that's one process or one pathway through this data analytics process. But there's actually others. So we could go back to that raw Wikipedia and instead get a discussion table, a table encoding which authors contributed to which table, or to which article. And now from that discussion table, we might induce a very different graph view, an editor graph encoding the relationship between contributors to the Wikipedia corpus. Now on that editor graph, we might run algorithms like community detection to identify the community each editor is a member of. And so we might render yet another table encoding the user and the community that they are assigned to. Now we're not done here because ultimately we want to bring multiple views together. And so we might actually ask, can we combine the PageRank analysis with the community detection analysis to identify the top communities on Wikipedia? Now in this story, we talked about multiple views of data. We looked at data as a table, and we also looked at data as graphs. And so when we think about building systems for doing this kind of analytics today, they're really sitting in two separate categories. We have separate systems for each of these views. For tables, we have data flow systems like Hadoop or Spark, which are really scalable and general purpose, are very good at processing this raw data and constructing tables. But when it comes to graphs, we've developed these specialized graph processing systems that are focused on graph structure computation, these iterative graph algorithms. And these are systems like Pregel, GraphLab, and Giraffe. Now the problem with having multiple systems is it can, one, be difficult to use. Users must learn, deploy, and manage multiple systems, and this can often lead to complex and brittle interfaces between multiple stages. Even worse, it can be inefficient. We have extensive data movement and duplication across each of these stages and across each of these systems. And in many cases, we're going to be building up and then tearing down similar representations of our graph. And so this can be, essentially, we have very limited reuse of the data across stages. So the work in GraphX is going to try to unify computation on tables and graphs. And we do that by exposing two separate logical views, a table and a graph view of our data, but then executing that on top of the same physical representation on top of the general purpose Spark data flow framework, enabling a single system to easily and efficiently support both types of computation. Now you might ask at this point, did we really need these specialized graph processing systems? Perhaps we could get rid of those and instead try to do everything in our generic data flow frameworks like Hadoop or Spark. And in fact, in our work in graph processing systems, we learned that there's a big performance gap in doing just this. So if we look at something like applying Hadoop to compute PageRank on the live journal graph, it takes, let's say, 1,300 seconds to compute a solution. GraphLab can solve the same problem in 22 seconds. So that's over 60 times faster. And that's a pretty big gap. Now everyone's probably saying Hadoop is a terrible thing to compare against. Maybe we could compare against a more contemporary in-memory data flow system, in particular Spark. So Spark is optimized for iterative computation, the kinds of computational patterns we see in graphs. It has in-memory support, so it should run much faster. And indeed it does, but it's still 16 times slower than this specialized graph processing system, right? And so ultimately this leads to the key question. How can we naturally express and efficiently execute graph algorithms in a general purpose distributed data flow framework? Now to answer this question, we're going to go back to the lessons we learned from these specialized graph processing systems and try to distill their essential ideas. And in particular, we're going to look at how they represent graph structured data, how they represent computation on graph structured data, and how they exploit these representations in the form of optimizations to allow them to execute graph computation efficiently at scale. Now, to understand that, I want to go back to our illustration of this analytics pipeline and focus in on the PageRank algorithm. And you can think of PageRank as sort of the word count of graph processing, the canonical algorithm that represents the core structure of the general class of computation. And so I'm going to put up an equation, but it's not a big equation. So this equation is going to describe the PageRank algorithm. And it has two key properties. One, the rank of a page can be expressed locally as a weighted sum of the neighboring pages. So it's a local property of the computation. And it is this property that will ultimately allow these systems to execute at scale and in parallel. There's also a key property that we have to iterate, that the rank of a page is updated as a function of the neighboring page's ranks. So as they evolve, we have to iterate until we reach a fixed point. So we have this iterative component. Now, to capture this pattern, there's this general philosophy of thinking like a vertex, which is essentially the description of the vertex program pattern used to describe algorithms on these kinds of graphs. And the pattern has this following simple form. Users define programs that live at each vertex, and those programs collect information about neighboring vertices in a stage called a gather. They use that information to update the vertex value, and then they send their new values to neighboring vertices. So this is what led to the gather, apply, scatter in the power graph pattern. Now, what's amazing is that this very simple representation of computation on a graph actually embodies a wide number of important algorithms. Algorithms in collaborative filtering, structure prediction, semi-supervised machine learning, community detection, and graph analytics, or more broadly, in machine learning and network analysis. So two important categories in modern analytics. Now, what we want to do is say, what can we learn from what do these systems in the graph processing systems learn from this special computational pattern, and how do they build special optimizations that exploit that pattern? And in particular, there's a range of key optimizations developed by these early graph processing systems that allow them to optimize execution on these kinds of graphs. So the first optimization is these specialized data structures that allow us to, on each machine, find the adjacent vertices of a particular vertex or the adjacent edges. And they're very compressed representations of the subgraph associated with that machine. In the power graph work, we studied the introduction of vertex cuts, a different way of thinking about how we partition graphs across machines. Rather than cutting along edges, we cut along vertices. And this change allowed us to efficiently execute very large computations on power law graphs, the kinds of graphs we see in the real world. Now, to exploit that partitioning of the graphs, we also introduced ideas in mirroring and caching, where we keep copies of vertices on remote machines so that we can reuse those vertices locally for all their adjacent neighbors. So a very simple caching strategy can have very big impacts in these iterative algorithms. Pregel introduced the concept of message combiners, a commutative associative way of combining messages that are destined to vertices on remote machines. And this structure can, again, substantially reduce communication across the network and exploits the graph topology. Finally, one of the key properties of the iterative algorithms on graphs is that the number of vertices that are actively changing on each iteration often decreases rapidly. So the active set of vertices is small, and these graph processing systems have specialized data structures to track the active set of vertices and focus the computational resources on those vertices. Now, in this work, in GraphX, we want to think about how we can reinterpret that representation and those optimizations in the context of this general purpose data flow framework. So when we think about representation, we're going to have to answer how we represent a graph as a collection of horizontally partitioned tables, how we represent the vertex programming model, these graph computational patterns, as general purpose join or data flow operators. And finally, how we're going to take that representation and exploit the optimizations previously developed in specialized systems in the context of this more general purpose data flow framework. In particular, we're going to have to recast those optimizations as distributed join optimizations and techniques in incremental materialized view maintenance. All right, so let me first talk about the representational developments we used in the GraphX system. So in a graph processing framework, we think of graph structured data as a property graph, a graph which has properties attached to each vertex and each edge. You can think of these properties as the page rank of a page or the user's profile, and the edge properties correspond to weights or maybe timestamps for that relationship. Now we want to reinterpret this graph as a collection of tables so we can encode it in our data flow framework. So the first thing we're going to do is actually pretty obvious. We're going to take the vertex properties and store them in a horizontally partitioned table. And so here I have a table which spans two machines, a logical representation of the collection of vertices partitioned by the vertex ID. Now, the other thing we're going to do is we're going to exploit the lessons learned in these specialized systems and how we partition graphs. In particular, we're also going to adopt a vertex cut approach, in which we're going to partition our edges across machines by using a vertex cut algorithm. And so we'll cut a subset of the vertices, and based on that cut, will assign the edges to separate machines. And that will actually lead to a horizontally partitioned table containing the edge properties. Now, in order to express graph algorithms in this normalized representation, we're going to need to join the vertex properties with the edge properties. And so we're going to need to do that repeatedly. And so we're going to introduce a third table called a routing table, which is going to describe where vertex properties will need to move in order to execute these kinds of joins. Now, this normalized representation has an important property. It's going to be a key attribute of how we're able to express iterative algorithms or support multiple graphs. So let me illustrate what I mean by that. Suppose I have some input graph, and I apply some transformation, perhaps an iteration of PageRank, changing the vertex properties. So I get a new graph, but in this new graph, the only thing that has changed is the vertex properties. And so I can actually reuse the underlying routing table and edge property tables. So I can reuse the structural information across changes to the attributes. And this is actually really important because in these bigger analytics pipelines, I might have many views of the same kinds of data and same subgraphs or different partitions of a particular graph. And so I'd like to be able to reuse as much as possible of my underlying data structures. So now, in addition to a wide range of general-purpose data flow operators exposed by the underlying framework Spark, GraphX introduces a logical view of a graph that binds this normalized tabular representation into something that looks like a graph data structure, so users don't have to think about complex joins on these many tables. In particular, this is the sequence of the core pieces of this graph API. We have an operator called graph, which allows you to construct a graph object, a horizontally partitioned collection of tables, as a function of an input vertex and edge table. And this operator is also going to verify that these edges are consistent with the vertices you've passed in. Now, once you have a graph object, you might have applied a graph algorithm, and you might actually want to ask for a view of the vertices, again, as a table. Now, this is just a logical view. It uses the same underlying physical representation. We can view the vertices and the edges as separate tables. In addition, we're going to introduce a triplets view, which is a logical joining of the vertex and edge tables. And I'll talk a bit more about that in a moment. We also have a collection of structural transformations, simple things like reversing the edges in the graph, or more important and powerful operators like constructing a subgraph, which will allow us to take a large graph, focus our attention on the subset of vertices and edges that are perhaps relevant to a particular computation, while actually reusing the underlying data structures from the supergraph. We have operators that allow us to join external tabular information with our graph, which is really important. We've built a big graph and want to include additional information described in other tables. And finally, we have this core operator, MapReduce triplets, which is going to be the essential piece that we'll use to express this vertex programming model defined in these specialized graph processing systems. So if we step back, the key operators that I really want to focus on today are the triplets operator and the MapReduce triplets operator. And so these are the operators that are going to embody this gather-scatter pattern that I described earlier. The triplets operator is actually very simple. We're going to take the vertex table and logically join it with the edge table. So for each edge in the edge table, we're going to attach the source and destination vertex properties with that edge. And we're going to do that for all the edges in the edge table. Now, given this logic representation of this join, we can now define a MapReduce operation on this subsequent table. And this, again, is going to be the way in which we express these vertex programs. So given this triplets table, we can use a user-defined map function and apply it to each of these triplets or edges, emitting a message to one of these source or destination vertices. And here we're going to constrain where we can send the message to allow us to build better indexing data structures, exploiting this graph topology. And so the user then defines a commutative associative reduction operator, which is a direct analog to the message combiners in a system like Prego. And these commutative associative message combiners allow us to sum the message destined to a particular vertex, incorporating pre- and post-aggregation across the network. Now, what's pretty exciting about this representation is actually using these basic operators, we can go back and implement these general systems like Prego and GraphLab in really under 50 lines of code, which is pretty amazing since I spent 4 years of my thesis writing 20,000 lines of code to my GraphLab. And then in less than a year, we can go rewrite it in 50 lines of code. But it's also a testament to being able to reuse the underlying system, so being able to build systems on top of other systems. Actually, what's even more interesting is that not only were we able to rewrite these existing graph processing systems, we actually found that some computation actually is better expressed in our simpler API. So things like triangle count or LDA actually can be expressed more naturally directly on these MapReduce triplets operators. So it's a pretty powerful set of primitives. So I've talked a bit about how we represent graphs and how we represent graph computation. Now I want to talk about the optimizations we introduced to enable something like Spark, a general purpose distributed data flow framework, to achieve performance parity with these specialized systems. So let's talk about the optimizations. All right, so the first and probably most important optimization that we introduced is the concept of a routing table. This is going to allow us to cluster edges however we like, introducing various vertex cut heuristics, but still be able to route the vertices to where they need to be in order to execute joins. So in particular, vertex A in this picture needs to be sent to both the blue and the orange machine, whereas the vertex B only needs to be sent to the blue machine. And the routing table encodes which machine I need to send each vertex to. So I only communicate vertices to machines that will be, that have edges that will play a role in that join. Now, one of the key ideas here, in a lesson learned from graph processing systems, is you never want to move edge information because the edge table can be orders of magnitude larger than the vertex table. And so the routing table effectively allows us to ensure that edges are fixed and we only route vertices across the network. Now, once we've used the routing table, we can now execute the join. And the way the join works is we ship the vertices to each machine. We don't go ahead and do the join initially. We actually place the vertices in a local reusable index hash. So we have a hash table on each of these edge partitions that we store the vertices there as a mirror cache, again, in direct analogy to these specialized ideas in caching for mirrored vertices in graph processing systems. Okay, so we have this mirror cache. And now, given this mirror cache, that's a hash index of these vertex properties, we can execute these MapReduce triplets operators by scanning the edge table and probing this local cache. So we have a very efficient way of representing the vertices. We're not duplicating them for each of the edges in the triplet. Okay, so we have this reusable hash. One of the things that I just mentioned earlier is this active set tracking property, where the number of vertices that are active in a given graph computation actually decreases rapidly. What that means is, if I look at my vertex table, maybe only a few vertices changed from the previous iteration. And so I'd like to be able to reuse the cache, and GraphX is able to track these changes in the vertex table, and then only ship the vertices that changed across the network. Again, reusing that mirror cache on the edge table. Now, we also track changes on the edge table and are able to switch between different scan strategies. So on the top table, only one vertex changed. So a graph algorithm on the top table is actually faster run by scanning the hash index and finding the adjacent edges using one of these specialized data structures. Now, on the bottom table, multiple vertices changed, and we actually found that it would be faster to scan the edges, again, probing back into the vertex table. And GraphX automatically switches between these scan strategies based on the number of vertices it changed in the edge partition. Okay, I said earlier we have a reusable hash index. As we do this scan, we're actually going to aggregate those changes locally, reusing that index data structure. And this is exploiting the fact that we've constrained the messages to be either to the source or destination vertices. Now we track those changes as we ship them back to the vertex table so that we can then iterate on this process using both these active vertex tracking techniques as well as these scan strategies. So now I've described some of the key optimizations. I want to talk about their implications on the performance of the system. So first, we get a reduction in the communication due to these updates. So here I plot the overall communication for the connected components algorithm. We see initially we communicate quite a bit, but as vertices stop changing, the active set tracking and the introduction of these caches allow us to reduce communication substantially. We can also look at the effect of these different scan strategies. Without switching between this reverse scan probe, this is the total runtime as a function of iteration. When we introduce the ability to switch between scan strategies, we see a substantial reduction in the overall runtime because we're able to probe the thing that's changing, or scan the thing that's changing least. Okay, and then finally, we actually introduced a new optimization not in the graph processing literature. In particular, we used join elimination. So we were able to identify when a map operation only used one of the or two of the attributes in the edge or in the triplet table. And so by doing bytecode inspection, we can identify that and simplify the join. And here again, we see a reduction by a factor of 2 in the overall communication. Interestingly, in the first iteration, there was no reduction. That's actually because all the messages are identical, and so the compression algorithm in the network was able to reduce the overall communication. There's a range of other optimizations, including techniques in lineage-based fault tolerance that I don't have time to talk about, so please ask me afterwards. All right, so finally, I want to talk about our system comparison. So the goal of the comparison was really to show that GraphX can achieve parity with these specialized graph processing systems. And to do that, we used a 16-node EC2 cluster, and we compare against GraphLab in PowerGraph, a C++ API, Giraffe, a Java framework, and Spark, a Java or Scala-based framework. So first, we look at the PageRank benchmark, which is a standard benchmark, on the Twitter web graph, or the Twitter graph and the UK Union graph. These are relatively large graphs. And the key takeaway here is that in both cases, GraphX performs about at parity with these specialized systems, while being about an order of magnitude faster than the general purpose Dataflow framework, implementing the exact same logical operators that we used in GraphX. We also looked at connected components, which is a slightly harder task, and we also see a similar pattern where GraphX performs at parity of specialized systems and is about an order of magnitude faster than the general purpose framework. Now, I've been talking a lot about these specialized benchmarks. I want to finally talk about what about a multiple stage pipeline. So here we look at the realistic task of going from Wikipedia hyperlinks all the way to the top 20 pages. And so if we look at a system like Spark, this runs in about 1,400 seconds. If we use these specialized systems in this intermediate stage, we can bring the runtime down. But by putting everything end-to-end in a system like GraphX, we get the shortest running time. And this is a small benchmark. As we go to longer pipelines, we expect to see much bigger wins. So I also want to briefly mention some of the adoption or the impact of GraphX. It is now part of Apache Spark. It's in production at Alibaba Taobao, and it's actually inspired some of the technology in my startup. And so in summary, GraphX unified tables and graphs. It presented an API that blurs the distinction between table and graph computation, a system that leverages advances developed both in general purpose data parallel frameworks and specialized graph processing systems, enabling a user to easily and efficiently express the entire analytics pipeline. And so one more thing I want to say, what did we learn? So we learned that using advances in specialized graph processing systems enabled us to, or leveraging advances in specialized graph processing systems enabled us to build general purpose frameworks for graph processing. And I'll end with that. Thank you.
Okay, we have time for a few questions. Go ahead.
Greg Hill from Stanford University. So you guys have some really awesome techniques for doing kind of analytics on static graph, but I was wondering how it works when the graph changes, not even like all the time, but let's just say that you want to do PageRank every day on the updated version of the Wikipedia graph. Is that something where you have to kind of throw out your old data set and all your cached values, or if only 5% of the graph changes, or can you kind of save some of those so that it's expensive the first day, but the second day it's faster?
Good. So what about changes in the structural or values of our graph? So within a stage, we don't actually currently support changes to the structure of the graph. So if I'm running some iterative computation, the introduction of changes in the structure would currently require changes in our routing table representation. But actually, there's a subtle difference or a subtle point there. When you construct a subgraph, we actually track the subgraph is reusing the underlying or the supergraph structure. And so we can support subgraph operations. But the addition of edges would require us to incrementally update that routing table. We have some techniques that are being developed right now to be able to support these incremental updates well within the lineage system of Spark. Yep.
Thank you.
Hello, Malte Schwarzkopf from Cambridge. So it's very exciting work, but especially because you can do this in a general purpose system, and it allows you to build these big pipelines. Mm-hmm. But there is another system that can do the same thing that was sort of a little bit absent from your evaluation, which is Naiad. And we've actually in Cambridge run some experiments with head-to-head comparisons of PowerGraph, Naiad, and Spark. We didn't test GraphX because it wasn't available at the time, but we found that Naiad is way, way, way faster than all of the other systems, including the specialized systems. So do you have any thoughts on whether your optimizations are comparable with those that the Naiad people made?
Good. So Naiad, actually, we talk a bit more about this in the paper. Naiad is a very powerful general purpose distributed data flow framework which incorporates asynchrony, something not available in Spark. I think the optimizations we described could actually be applied on top of Naiad. And in fact, Naiad has some of the same representational ideas. And in fact, Naiad has one additional optimization that we haven't described here, which is a way of representing the edges within each machine using Hilbert space filling curves. But still, I actually think if you look at Naiad, they have a system called GraphLink, which is more analogous to GraphX, although it's just been recently announced. So I don't actually know the details of the optimizations they do in that at this point.
All right, thank you.
Yep.
Great, one more question.
Menak Ghosh, UIUC, nice work.
Thank you.
Just one question, so you compared with GraphLab. Is it like the original C++ implementation or on top of Spark?
Good. So when we compared against GraphLab, it was my code, so I actually spent quite a bit of time hacking it to make sure it would work comparably on the EC2 cluster that we were running Spark on top of. It was the true PowerGraph 2.2 code with the Warp engine added, which was a later contribution by one of my colleagues from CMU.
Okay. just to follow up on that, like, did you explore some of the, like, some of your new optimizations? Can they be ported back to Paragraph and like other comparison equivalent?
Very good. So the question of how can we bring back some of the ideas we learned here into a system like Paragraph, indeed we could have pulled some of these materialization strategies back should GraphLab actually allow us to read the bytecode or the binary of the individual user-defined functions. So there are some techniques here that could in theory be put into GraphLab. We probably won't be able to do that in the near future because of the sort of lower level design that GraphLab took in the system.
All right, let's thank the speaker again.
Thank you.